Alright, in the second example of shear moment diagrams, variation of internal shear, internal bending moment along a beam. We got the cantilever beam. We've seen this one before. We derived what the variation of the shear and the moment would be. Here we already have found the reactions, and once again we'll just use our understanding of what it means for a slope to be a certain value and what a change will actually represent. Right, so we're going to start off at zero shear. We'll follow the concentrated force because it creates a discontinuity in the shear. So we start at zero, we go downwards following that direction of that concentrated force. There is no distributed load, so the slope then dv dx equals 0. Bam, so we draw that. And there's no change in the shear, then we end up at a minus 20 on the far right side. Then we have another concentrated force that represents the reaction. That closes us back off to 0 exactly like we should. Start at 0, end at 0, always. Right? Same thing with the moment diagram. Start at 0, end at 0, but how do we get there? Well, we start with a little smiley face, positive 100. So we immediately shoot up to a plus 100. Right? Now, the slope of the moment diagram is given to us by the value of the shear. The shear is negative, so therefore we're going to have some sort of negative slope. It's just a question of, and the slope is a constant value, so that'll be a straight line all the way through. It's just where do we end up? Well, minus 20 times the length of our kips times 20 feet is going to be a minus 300 kip foot. That's units of moment. That's what this little business is all about right here. So we start at 100, we subtract off 300, and we end up then at minus 200. And then note that matches then this little frowny face 200 that we have here. Now, the other thing to realize is a clockwise moment actually creates a positive discontinuity in the moment diagram. That's what's really happening here. So we're at minus 200 and we have a clockwise that gives a positive 200, and so that jumps us back up to 0. Start at 0, end at 0. Now one more thing, we're crossing here from a positive to a negative moment, and that's happening in this case at, then we can tell by similar triangles, at the 1/3, 2/3 location, and that tells us all kinds of things about the curvature of the beam. Remember, positive bending moment is smiley face, negative moment is frowny face. So over here at this fixed end, where the beam is got no rotation and it's got no displacement, that means we would draw in here a frowny face going about down to here, and then we have a transition point. This is at 0 moment at x equal to 5 feet, then that is an inflection point. It means we're going to change from the frowny face to smiley face. Now I don't know if the end of the beam ends up actually going up a little bit or if it ends up going down a little bit. I don't really know, but qualitatively we have a curve that matches the displacement boundary conditions here, matches the curvature, and that's all that is required in our system. Right? Bam. That quick, that easy.